Welcome to our channel, and today we are going to help you understand the paper MEDITRON-70B, Scaling Medical Pre-Training for Large Language Models. The abstract describes the creation and release of MEDITRON, a suite of open-source large language models, LLMs, specifically tailored for the medical domain, developed by a team primarily from EPFL. MEDITRON comprises models with 7 billion and 70 billion parameters and is based on the Llama 2 model, which has been adapted using NVIDIA's Megatron-LM distributed trainer. The team pre-trained the models on an extensive and selectively curated medical corpus, including PubMed articles, abstracts, and established medical guidelines. Upon evaluation using 4 major medical benchmarks, MEDITRON showed notable improvements in performance. The abstract highlights that MEDITRON has achieved a 6% absolute performance increase over the top public baseline in its parameter class and a 3% improvement over the highest baseline fine-tuned from Llama 2. When compared to closed-source LLMs, MEDITRON-70B surpasses the performance of GPT 3.5 and MedPalm and is competitive, within 5% of GPT-4 and 10% of Med2. A specific achievement of MEDITRON-70B is an accuracy of 70.2% on MedQA, a dataset that includes USMLE-style medical questions with 4 possible options. The team has made both the code for creating the pre-training medical corpus and the model weights of MEDITRON available to encourage further open-source development of sophisticated medical LLMs. The paper associated with this abstract is a preprint and is under review as of November 27, 2023. The text provides an introduction to the medical reasoning capabilities of MEDITRON, a large language model, LLM, designed for medical applications. MEDITRON has been developed by training on high-quality medical evidence sources, aiming to provide equitable access to medical knowledge for clinical decision-making. Despite the advanced capabilities of LLMs to replicate human decision-making traits, they have traditionally been evaluated on general tasks using diverse internet-sourced datasets. However, task-specific LLMs trained on curated datasets have shown better performance. The authors of the text present MEDITRON-7B and MEDITRON-70B models, which were adapted from the Llama 2 architecture using a training library called Megatron-LM. These models were further trained on select medical sources, such as PubMed, to improve their medical reasoning. MEDITRON was assessed on 4 medical reasoning benchmarks, where it performed better than other similar models, showing advances in medical reasoning capabilities. However, the authors caution against using MEDITRON in real-world medical settings without further alignment with specific use cases, additional testing, and randomized controlled trials to ensure safety and professional applicability. The text discusses MEDITRON, a system for scaling medical-specific pre-training for large language models, LLMs. The authors propose an optimized workflow that involves knowledge-based data curation, continued pre-training, fine-tuning, few-shot in-context learning, and advanced inference methods like chain-of-thought reasoning and self-consistency. These methods improve performance on medical reasoning benchmarks, surpassing prior baselines. The researchers provide the community with access to the curated training corpus, distributed training library, and MEDITRON models, both 7B and 70B parameter sizes, with and without fine-tuning. The medical training data for MEDITRON, known as Gap Replay, consists of a 48.1B token corpus from 4 datasets. A new clinical guidelines dataset containing 46K articles from 16 recognized sources, abstracts from 16.1 mem closed access papers on PubMed and PubMed Central, full-text articles from 5 mem public papers on PubMed and PubMed Central, and a replay dataset constituting 1% of the entire corpus. Clinical practice guidelines, CPGs, in the corpus are evidence-based recommendations for healthcare practitioners and patients coming from various global and organizational levels. 35,733 guideline articles from 8 out of 16 sources are released publicly, along with web scrapers and pre-processing code for all 16 sources for the collection and processing of clinical guidelines, criteria selected for open access, homogeneous textual structure, English language, and coverage across medical subdomains and different resource settings were used. Data was cleaned to exclude non-contributory content and standardized for consistency. Deduplication and filtering ensured the high quality of the corpus. The pre-training corpus and tools are made publicly available for further research and application in medical LLMs. The text provides an overview of a data mixture used for pre-training a large language model specifically aimed at the health domain. It describes the datasets included, their sizes, and the processing techniques applied. The data mixture, referred to as gap replay, consists of various sources. 1. Clinical guidelines. This part of the dataset comes from various geographic and resource settings, including international organizations such as WHO, national authorities like CDC and NICE, regional entities, and institutions. It addresses a broad spectrum of healthcare issues, possesses a mix of technical and conversational language, and targets both clinicians and patients across specialized themes. PubMed papers and abstracts. Constituting the largest part of MEDITRON's pre-training mix, this corpus includes millions of full-text papers and abstracts from PubMed. These texts cover extensive biomedical information, and the dataset is compiled from the S2ORC and PubMed Central Open Access subset, including papers and abstracts not found in S2ORC with a knowledge cutoff of August 2023. Processing PubMed data involved removing metadata, references, and other non-textual elements. In-text citations were reformatted using special tokens similar to the Galactica model to facilitate accurate citation use by the model. Hierarchical structure was promoted by marking section headers and prepending paper titles to the body text. Non-English articles and duplicates were filtered out. Experience replay. This is a method used to prevent catastrophic forgetting by including data from old tasks when training on new tasks. The text does not provide further details as it seems to be cut off. In summary, the text outlines the composition and pre-processing of a large-scale medical text dataset intended for the training of a health-specific language model, emphasizing the diversity of sources and the importance of structuring data to optimize model learning. The text discusses the challenges and solutions involved in training large language models, LLMs, on a significant scale, focusing on the MEDITRON project's approach to preserving pre-trained knowledge and efficiently managing large-scale distributed training. To prevent the loss of knowledge from the Llama 2 model, researchers added general domain data from an open-access dataset called Red Pajama, which is a mixture of various corpora, including the Falcon Refined Web Corpus, the StarCoder dataset, Wikipedia, Arxiv, Books, and Stack Exchange. This mixture accounted for 1% of the total data and constituted 420 million tokens. The engineering challenge of training LLMs is addressed by using the Megatron LLM Distributed Training Library. This library, which builds on NVIDIA's Megatron LM framework, enables the use of multiple GPUs across many computation nodes, employing multiple forms of parallelism for efficiency, including data, pipeline, tensor, and sequence parallelism. Advanced techniques like activation recomputation to save memory, fused operations, and support for the rotary position embedding, grouped query attention, and other architectural innovations facilitate training large models, specifically Llama, Falcon, and Llama 2. MEDITRON models are trained on an in-house cluster with 16 nodes, each with impressive hardware specifications, including 8 NVIDIA A100 80GB GPUs. Network efficiency is critical due to distributed training across many GPUs and computation nodes. The network infrastructure relies on RDMA over Converged Ethernet and NVLink and NV-switch technology for intranode GPU connection. Model parallelism efficiency was evaluated, and the researchers found that using tensor parallelism equal to the number of GPUs per node, 8 in their case, yielded the best results. For their largest model with 70 billion parameters, they employed a balance of pipeline and data parallelism, PP and DP, with small batch sizes to manage memory constraints and maintain high performance. They also confirm that 3D model parallelism, TP, PP, and DP all greater than 1, is crucial for efficient training at this scale. However, it's mentioned that the cluster's low internode bandwidth impacts certain forms of parallelism, such as pipeline parallelism. The text describes a study involving the adaptation of the Llama 2 language model for use in the medical domain. The adaptation process involves continued pre-training on a custom medical dataset called Gap Replay. This dataset includes various medical texts, such as papers from PubMed, medical guidelines, and replay data. Key training details include using the Atom W optimizer with a cosine learning rate scheduler, maintaining the standard transformer architecture, and adopting the SWIG-LU activation function and GQA from the original Llama 2. Two versions of the pre-trained model, MEDITRON-7B and MEDITRON-70B, are used with different context lengths and optimization parameters. Notable achievements include efficiency in terms of model flops utilization when compared to other models of similar sizes. Hyperparameters and tokenization are detailed, with mention of beta values for the optimizer, steps for warm-up, learning rates for different models, and the byte pair encoding (BPE) algorithm used in the tokenizer. For supervised fine-tuning, the authors evaluate their models on medical reasoning benchmarks, finely tuning on specific benchmark training sets, such as MEDMCQA, and testing on the corresponding test sets. For benchmarks with no training set, such as MMLU, the model is evaluated with fine-tuning performed on related datasets. The text describes instructions and implementation details for training a medical-focused AI model called MEDITRON. Instructions for different benchmark datasets, MEDQA, PubMedQA, and MEDMCQA, are provided to assess the model's understanding of medical knowledge and its application in answering questions typical to medical licensing exams. The instructions also specify that answers to the multiple choice questions must be based on current medical guidelines. For the implementation, the text follows the formatting guidelines outlined by OpenAI's ChatML, including the use of special tokens to structure the interaction between user and assistant roles. During training, the model's loss is calculated only on the response tokens. An example illustrates how a prompt is formatted for fine-tuning on the MEDQA dataset, where the model is expected to choose the correct answer from multiple options based on medical guidelines. The correct answer for the given example is identified as cystic hygroma. The fine-tuning process uses the Atom W optimizer with specific hyperparameters and a cosine learning rate schedule. The described approach also involves a warm-up phase and a decay of the learning rate. Training is carried out over 3 epochs with a specified batch size and weight decay value, following practices from a related work. In short, the text provides a detailed explanation of the process for training and fine-tuning a medical AI model on a set of benchmarks assessing medical knowledge through multiple choice questions, using specific formats and hyperparameters to optimize performance. The text discusses various medical benchmark datasets and inference methods used to evaluate a model named MEDITRON. 5 medical benchmark datasets are mentioned: MEDQA, MEDQA4 option, PubMedQA, MEDMCQA, and MMLU medical. Each dataset varies in the number of training and testing samples, the format of questions, and the number of answer choices, and all are multiple-choice question-answering tasks. To evaluate models, the text describes the use of different inference methods. Top token selection, top token, involves using a text generation engine to produce the next token output and select the token with the highest log probability as the answer. Chain of thought, CoT, prompts the model to show intermediate reasoning steps, and self-consistency SC generates multiple reasoning traces and uses majority voting to select the final answer. MEDQA is specifically highlighted as it's styled after the U.S. medical license exam and involves a combination of different medical knowledge areas. It is a challenging dataset with 10,178 training questions and 1,273 test questions. MEDQA includes a 5-option and a 4-option variant, with models being trained on the former and evaluated on both to ensure comparability in assessing medical LLMs. No explanatory answers are provided in this dataset. Therefore, another set of questions with human written explanations is used for fine-tuning models for chain-of-thought reasoning. The text discusses the results of experiments comparing the few-shot learning performance of MEDITRON models with other models on various medical-related tasks. Few-shot learning refers to the machine learning technique where a model is trained to learn from a very small amount of data. In the summary of the results presented in Table 4, the MEDITRON models, which come in 2 sizes, 7 billion parameters and 70 billion parameters, show performance in medical tasks without additional fine-tuning with task-specific training sets. The experiments show that for 7B models, 3 examples from the training data are used for learning, 3-shot, while for 70B models, 5 examples are used, 5-shot. Several datasets were used to evaluate the models. MMLU Medical, a benchmark that combines medical-related questions from various subjects. PubMed QA, a dataset that requires models to answer yes, no, or maybe to questions given a PubMed abstract as context. MedMC QA consists of multiple-choice questions from Indian medical entrance exams. The text notes that the MEDITRON models are compared to other pre-trained baseline models like Llama 2, both 7B and 70B, and PMC Llama 7B, which have not been pre-trained further. The authors of the study report average accuracy across 3 different random seeds they used for sampling the few-shot demonstrations. The 7B MEDITRON model and the 70B MEDITRON model both outperform the baseline, indicating the superior few-shot learning ability of the MEDITRON models in medical tasks. The text provides a comparative analysis of various medical models on their performance in downstream medical tasks. Specifically, the performance of MEDITRON models, MEDITRON-7B and MEDITRON-70B, is compared to other open-source medical models. The performance metrics used are accuracy levels on medical benchmarks such as PubMed QA, MedMC QA, MedQA, and others. Models pre-trained on non-medical data receive additional pre-training or instruction tuning on medical data to measure their efficacy. Key findings include MEDITRON-7B with in-context learning shows substantial improvements over other pre-trained baselines, especially with a 20% performance increase on PubMed QA. At the larger model scale 70B, MEDITRON-70B and Llama 2 70B see significant performance increases, with MEDITRON-70B surpassing all benchmarks against the base model. Models at the 70B scale show competent reasoning abilities on medical tasks even before specialized task fine-tuning, with MEDITRON models performing particularly well. For the PubMed QA benchmark, the in-context learning performance of a model almost matches the performance of a fine-tuned model on the same data. The text also explains that the models were fine-tuned on available training sets and that different prompting methods, such as zero-shot chain of thought and self-consistency chain of thought, were used. It is noted that the human passing score on MedQA is 60.0, and certain models achieved this threshold. Pre-trained models from general benchmarks and methods of inference using top token selection and various prompting techniques are discussed. The overall gist is that continued pre-training on medical data allows the models to perform better on medical benchmarks. The text describes a comparison of the performance of a language model called MEDITRON-70B against several large commercial language models, LLMs, on 4 medical benchmarks: PubMed QA, MedMC QA, MedQA, and MedQA4 option. The commercial LLMs being compared include GPT 3.5, GPT-4, and 2 versions of MedPalm, all of which have significantly more parameters than MEDITRON. The LLM's results are cited from associated papers, and it is noted that certain LLMs do not report performance on some benchmarks. MEDITRON and other models, like Llama 2 and PMC Llama 7B, were specifically fine-tuned on the training sets of the benchmarks, unlike some public baselines that were excluded from further supervised fine-tuning because they had been previously instruction-tuned on the data. In terms of 7B scale models, MEDITRON-7B outperformed similar scale models, even outstripping some state-of-the-art instruction-tuned models with significant performance gains, especially on PubMed QA. Results show that MEDITRON-7B achieves the highest accuracy on the medical benchmarks compared to the other models, particularly with 70.4% on PubMed QA and over 10% better performance than competing models. At the 70B scale, MEDITRON's performance is not detailed, but the comparison involves instruction-tuned models, and MEDITRON-70B also competes against larger commercial LLMs. Overall, MEDITRON models fine-tuned on individual benchmarks demonstrated competitive or superior accuracy on those benchmarks compared to other surveyed models. The provided text seems to be discussing a research analysis of the MEDITRON-70B model's performance in language modeling tasks, particularly within the medical domain. This analysis showed that the MEDITRON-70B model outperforms other models, such as Clinical Camel 70B, Med42 70B, and fine-tuned Llama 2 70B, in both training and validation loss, indicating better performance in understanding and generating medical language after being pre-trained with billions of tokens. Moreover, the implementation of chain of thought, COT and self-consistency chain of thought, SCCOT, cognitive techniques has further improved model performance, with SC-COT providing the highest boost. MEDITRON-70B was able to surpass human passing scores on medical question answering benchmarks, such as MedQA. Interestingly, it competes well with commercial language models, LLMs like GPT 3.5, GPT 4, and MedPalM variants, even having fewer parameters than these larger models. The text also references a figure showing the decline in training and validation losses during the Metatron 70B pre-training process, which confirms the model's ability to learn effectively without overfitting. Intermediate checkpoints at different iterations, 5K, 10K, 15K, were used to evaluate performance on medical benchmarks in a 5-shot in-context learning setting, although specific results from these evaluations aren't detailed in the summary provided. Overall, the analysis promotes Metatron 70B as a competitive model for medical reasoning tasks, able to outperform other models and exhibit high accuracy across various benchmarks despite its smaller size compared to some commercial LLMs.